All right, welcome everybody. Thank you for tuning into this webinar. My name is Mark and I work as a technical lead at a company called Edument, based in Sweden. I'll be presenting for roughly 45 minutes and then we'll have time for a short Q&A afterwards. And please, if you have any questions, you may write them in the chat and we'll get to them during the Q&A. You have also in the chat a link to the sample code that I will go through in this webinar, and also my contact details if you would like to reach out to me afterwards. This talk is about designing and implementing robust web apps with the help of a library called XState, which allows us to more formally describe, I would say, model the various states and events that constitute the behavior of the various front-end environments we're building. So what do I mean by the term modeling? Are we talking something like UML and sequence diagrams? In a sense, yes, in that we'll be introduced to a formal language of sorts called state charts, as well as visual tools that will help us in the modeling process. But I want to begin with setting forth an overall objective for this talk. And that is, very simply, to ensure that bad things do not happen. I would hasten to add, when our application is in a certain state. Now, this may sound simple enough, but I'm sure you've also experienced that actually achieving this can be really hard. So as a personal example, I was recently involved in a large-scale WebRTC project where we had to handle a large amount of application logic and complexity with a multitude of states and events. And we reached a point where we simply had to take a step back to figure out a way to properly model everything that was happening in order to achieve this very simple objective that we've outlined. And it was especially important because we had to ensure correctness and robustness as the application targeted a medical community with stringent requirements. So with a lot of state and events, we naturally turned our attention to state machines. So what are state machines? Or as they're fully named, finite state machines. Wikipedia sort of summarizes it as a mathematical representation of the flow of state over time. We won't be delving into the math behind state machines. We'll simply observe a few properties. A state machine has a finite number of states and events. It also has a mapping of state transitions, how we navigate from one state to another as events occur and trigger these transitions. And a state machine also has an initial state when it starts up. Now you can augment this basic kind of state machine with something called state charts. I would basically describe them as additional abstractions, extensions for modeling stateful systems. Now, the good thing is that the XState library implements all of this, which is very convenient for our purposes. So let's take a look at what a state machine is with an example where we would like to model a task executor. Basically, we want to implement a state machine that allows us to schedule a task, for example, fetching some kind of data, and execute the task, and also be able to observe the various states and events that happen as our task is run. So if we spend some time and think about a task executor, we'll end up with a list of states and events that are presented here in this table. These transitions between events are not mapped out here, but for example, if we have a state machine that starts in an idle state and the task executor receives a task to execute, we'll see that we'll transition via an execute event to the pending state. And if a task completes successfully, we receive a done event, which transitions us to the success state. There's also additional data that a state machine in this case has to manage. And that is, for example, the result of the task, if it completes successfully, or the error object, if we happen to end up with a failure. Now, to build a model of this state machine, we can turn to what's called the XState visualizer. So XState is not only a library implementing certain formal concepts, it also provides us with a tool, a visual tool, that allows us to define a state machine and also see it represented visually. So to the left here, you'll see the state machine as it exists right now, and you probably identify some of the states and events that was presented previously. And here to the right, we have the actual state machine. And well, the state machine is nothing more than a sizable JavaScript object. And even though it might look like a lot at first glance, it's actually pretty intuitive. So let's step through this state machine definition and investigate its contents. So a state machine in XState has an ID. We can define contextual data that the state machine ought to manage. And in this case, we have the value of the result of the task if it completes, or the error object if it fails. So this is additional data that the state machine manages in a so-called context. The state machine starts off in a idle state. Remember, a state machine starts off in some type of state. And then we have a property called states, in which we simply define all of our states one by one. So we have an idle state, we have a pending state, a success state, and a failure state. So in the idle state, for example, we can register that we are listening or expecting an execute event. And if such an event is sent to us, sent to the state machine, we will transition the machine to the pending state. Now, when we enter the pending state, we can fire a so-called effect. In this case, a reset effect. And this type of effect is called an action. An action is a synchronous thing, a synchronous effect. And what we do here is we update the context by resetting it. So in preparation for running a new task, we reset the context, which carries a value and error field. Now, this is an identifier, a name for our action. And the actions are themselves defined a bit below. So if we scroll down, we'll see that another part of this definition where we define actions. And in this case, we say that the reset action simply resets the value and error fields. And we're using an assign method from the XState library to achieve this. So we reset the context upon entry to the pending state. Next up, we invoke a service. And a service is an asynchronous effect. So an asynchronous effect triggers an asynchronous call of some sort. And in this case, we refer by an identifier to the actual task executor, the task executor service. But it's not defined here in the definition. We'll provide the actual implementation later on in our application. For now, we simply say that there is a task executor service to be expected, and that's what the state machine will target. And this service, this task executor service, will send back events to us, to the state machine, upon some sort of completion. If it completes successfully, we receive an undone event. And in that case, we transition to the success state. And as part of that transition, we also fire another effect, an action called handle success, in which we update the value, the result. If we receive an on-error event, well, similarly, we transition to the failure state. And we need also to update the context to indicate that an error has occurred. So this is basically the entire inner workings of the machine, except for the actual implementation of this task executor service. Now, let's step through this state machine one event at a time. So we begin in the idle state. We receive an execute event to execute a task. And you see we enter the pending state. Let's say that we complete successfully. We receive an undone event. This takes us back, or takes us to the success state. And in the success state, we can receive a new task to execute, and that will lead us back to the pending state. And the pending state may, and the task in the pending state may fail. We receive an error event, transitioning us to the failure state, from which we again can execute the task. So using this description, this definition of a state machine, and this visual rendering of that definition, we're able to design, visualize, and test the entire test machine in one tool. We can actually extend the state machine with a few things. For one thing, let's make it so we can cancel a task. To cancel a task, well, we want to be able to cancel a task while it's pending. So we'll move over to the pending state over here. And we'll say that we would like to be able to register for a cancel event, in which case, if it occurs, we'd like to take us back to idle. We update the rendering, and we see now that a cancel event has been added. So we execute a task, we end up in the pending state, canceling takes us back to idle. So we've captured that logic. Right now, there is no way to cancel a task and execute a new task while a current one is running. So we can cancel one task, but what about actually executing, putting in a new task to this task executor while one is already pending? We can do this. We can execute a second task if the first one is currently pending, canceling the first and then running the second one by adding a few more things to this machine. We'll need a way to identify a task. So I'll add to the context an identifier for our current task. Next, we should be able to execute a new task while in the pending state. So as part of the pending state description, we'll add execute event. And we'll say that if we receive an execute event for a new task while in this state, we would like to exit and re-enter, but with the new task. So our target will be the same state, namely pending. So we'll exit and then re-enter, but this time with a new task. But it really has to be a new task. So this transition will be conditional. We'll add a condition to this transition. And the syntax is easily looked up in the documentation, but basically we want to compare the task that is currently running, that is stored in our context, and make sure that it differs from the task that is now intended to be run. And that task ID we receive as part of the event. If this condition is fulfilled, we will exit the pending state and then re-enter, but this time we'll do it with a new task. And we have to remember as well that we need to make sure that our task ID is updated correctly as well. So we'll add a little bit of logic to our reset action. Remember, this one resets the context, but we will reset it in preparation for running a new task with the task ID that we received as part of the execute event. So now we'll always have an ID coupled to the task. Let's update this one. I think I forgot a comma. There we go. A few changes have been made. Well, let's try this. We execute to the pending state. We still are able to cancel a task and then successfully complete or receive a failure. But there is something about a condition now. Let's try this out. We can move over to the event panel here. And we can try this. If we reset this state machine, we'll add a task ID of 1. We'll send this to the machine. Properly formatted. So by sending an execute event with a task ID of 1, we enter the pending state. Let's try to send the same event with the same task ID. Doesn't really trigger something. But if we change the task ID, you notice that it flashed briefly. That means we exited and re-entered the pending state, but this time with a new task. We can see this because in the context, we now have a task ID of 2. Let's try the task ID of 3. Send it. Briefly flashed, indicating that we've accepted a new task. And the task ID is now updated. So this is our way of making sure that our state machine behaves and models the intended application behavior in the right way. Now, let's take this definition and then try to apply it in our React app. We have a web app, which the state machine is intended to be used in. So what we'll do is simply copy all of this and paste it into our app, something I've already prepared. So you would simply copy all of this, and then you would move over and paste it into your application. So in the sample code, we have a task example for our task executor. And I have a file, task machine, which will contain this definition, but it's simply a copy-paste procedure. nothing more. So having verified the model in the visualizer, we copy paste it into our application. And now we can use some clever XState React bindings to put this to use. So in our app component, which renders our app, we are utilizing a use machine hook from the React bindings. And to this use machine hook, we pass the machine, the actual state machine that we just copy pasted. And we augment, extend this machine with the actual implementation of our task execute. Remember, in our model, we only have an identifier for this service. In our application, where we actually implement the service, this is where we extend the definition with that implementation. We have a few event handlers here. So when we submit a task, we simply, as we saw previously, we send an execute event, and together with the task ID, in this case, our task ID is the actual URL of a user that we want to fetch. We can also cancel a task, in which we send simply a cancel event to the machine. And this send function is something we receive from the use machine hook. We also get a state object from the use machine hook. This is useful because we can use that object to determine what to render, depending on what state we're actually in. So in this case, we can match on certain states and render something appropriately for the current state that we're in. And that's basically it. So let's see this in action. Here we have our application where we can enter an ID for a user and then fetch it. And it just so happens that if you have the XState dev tools installed, an extension to Chrome, you get the entire state machine visualized while the app is running. So I'm also gonna slow down this app for a bit so we can follow along. So let's try to fetch a user and observe what is happening below in the state machine visualization. You saw a brief number of flashes, but basically the state machine is updated in this visualization as things are progressing with our task. Let's try it again. Pending, done, success. If we try to fetch a user and cancel, we transition back to idle. Let's see what happens if we try to fetch the same user multiple times. I'll go over to the network, clear log. I'm gonna click the fetch user button and I'm gonna click it a few more times to see what happens. Let's take that again. Fetch user. Even though I tried to fetch the same user multiple times, the state machine prevented me from actually doing it because that type of state transition is not allowed while I'm in the pending state. So if I try to fetch the same user, remember we had a condition checking for this, the state machine will not allow me to fetch the same user multiple times while a request has already gone out for that user. What happens if we try to fetch one user and then immediately try to fetch a second one? We'll start by fetching user number 2, and then increase and fetch user number 3. Well, turns out we canceled number 2 to fetch number 3. Again, our condition ensures that if we actually want to fetch a new user, there's a new task to be executed, we will cancel the current one and then let the new one be executed. So this is actually working quite well. And the state machine makes sure that everything goes according to plan. Specifically, this button doesn't have to be disabled, as you've probably noticed. We could disable it, but it doesn't have to be, because we are safe in our knowledge that the state machine will prevent any bad things from happening. Again, trying to reach our overall objective. So, what are the takeaways from this example? Well, XState, both as a library and as a tool, allows us to define, visualize, try and test our state machine out, and gives us what we need to actually implement them in our apps. This is a comprehensive solution for all things state machines. And there are a few terms that we observed. These, again, are parts of these state machine extensions. So we saw effects, actions that simply update synchronously our context, and services, our actual task executor, which is an asynchronous effect. We observed something called a context, where we store, you might call it extended state. Sort of a parallel could be if you have a car that might have 3 different states: reverse, neutral, and drive. Those are our actual states, whereas the amount of gas in the tank, that's extended state. That's something that belongs in a context. That's more of a continuous type of data. And then we saw guards, or conditions, that we can implement to conditionally transition from one state to another. I mentioned I was involved in a pretty complex project recently, a WebRTC application, and I wanted to give a short overview of what you might encounter when you're using state machines in a large-scale application. So in this project, we had a lot of things to consider. The project itself had to deal with web clients trying to interact in various ways with users of augmented reality devices. You would have a user with an AR device, a phone or glasses, interacting with a number of web clients. And the issues to consider range from connectivity, actually handling network conditions, managing sessions and users coming and going, streaming audio and video, and supporting a lot of different interactivity features for web clients. So a lot of things going on at the same time, and something that drove us to using state machines and XState to ensure correctness and robustness. I wanted to show a simple model of some of the few issues here. The model doesn't cover everything, but it sort of gives you a hint of what was involved in this scenario. So let's move over to the second state machine. And this is a state machine sort of simplified for the project I was working on. Again, following along with the same principles of how you define it, we have a number of states that have to do with connectivity: disconnected, connecting, and ending up in a connected state. And in the connected state, you can actually have several substates. This is another important feature of state machines. Once in the connected state, the nested states further detail the behavior of your application. So if we trace the transitions, connecting successfully, ending up in the idle state, in the overall connected state. So we're able to have sort of a granular definition of what it means to be in a connected state, connected and idle. Now, once in the idle state, I, as a web client, can receive an invitation to a call from a host. So receiving such an event allows me to transition to a pending state, again, within the overall connected state. I can accept the invitation, which transitions me to the nested call state. And the call state is itself pretty interesting, because if you look at the definition, the call state, which is nested under the connected state, call state is of type parallel, because it has two parallel states. They are not dependent on each other. They're not nested, but they are active at the same time. I have a state management for sessions for dealing with people coming and going from the group or channel I'm in. And I have a separate state definition, or part of the state definition, dealing with the audio and video streams being created, deleted, and so forth. So within the call nested state, I have two parallel states, each dealing with their own state logic, because trying to merge everything into one big whole would be too complicated. This is another way to structure your overall state management in a more convenient, efficient manner. And once I've joined a session, I've joined a call, I can leave a call, take me back to idle while still connected, but I can choose to disconnect entirely from all operations, which brings me back to the initial disconnected state. So a bit more going on, but the important two takeaways right now are nested hierarchical states. We can be in an overall connected state, and within that connected state, there are several substates that we can transition between. And we also have the notion of parallel states, which are independent but active at the same time, each dealing with their own facets of the overall behavior of our app. So this might look a bit complex at first sight, but it's quite intuitive once you start working with it, and not too it requires a sort of a upfront investment in learning to work with this tool and library, but the reward is significant, especially in larger projects. I do have time to tweak the state machine a bit. So let's try to see if we can handle network interruption in our state machine. We only have the successful states right now where we successfully connect or, well, fail to connect. But what if we're in a session, in a call, and we suddenly get a network interruption? Well, let's see what we can do in that case. There are several ways to handle this. One way is to split up this connecting state into two substates. You can call it initial and retry. So let's begin by changing the structure of the connecting states. So under connecting, I'm going to add two substates. I'm going to call the first one initial and the second one retry. And in the initial substate, I'm going to listen for this event. Connect success. So I've moved it into the substate. And I'm going to have to be more specific here because we're sort of nested right now. So we need to be more specific in terms of targeting other states on this level. So I'm going to say that I'm actually targeting the connected state overall, which means this one. But I have to prefix it to make things work. Agora is the ID of our state machine. This is a minor detail, but if you're wondering, this is more to be more fully qualified in targeting the state. So there we have that part. And when we're in the disconnected state and we want to connect, we're now going to say that we want to transition to connecting .initial, the initial substate of the connecting state. So we want to transition to this state, this substate, upon first connecting in the app. Okay, let's try to update this. Then we get something that looks like this. We can connect. We end up in the initial connecting state the first time we do this in the application. We receive a successful connect, and we end up in the idle state. So basically the same thing as before, but we have sort of a middle nested state called initial that we have to go through in order to end up connected in the idle state. Now, this is due to the fact that we want to implement or define, I should say, network interruption, the logic to handle it. So let's see what can happen if such a thing occurs in the connected state. So here in the overall connected state, we can disconnect, or can also, let's say, receive an interrupt event, a network interruption event. And when that happens, let's transition to a connecting state, but in the retry substate. So we're attempting to retry the connection. And this is the substate we're talking about. And here, if we do successfully retry to connect, it will be quite nice if we can sort of end up in this state that we were in previously. So let's not go back to just being idle in terms of reconnecting. Let's transition back all the way to where we actually left, which might be in a session, in a call. So I want to be more specific here. I'm going to say that we're connecting or transitioning to the connected state. I'm going to dub it hist for history. We're going to transition back to a state which remembers our history to reflect where we left off, where we were before we were interrupted. And adding a history event isn't all that involved. We simply add at the end of the connected state, which would be here. We call this a history event. So we added something called a history event at the end of the connected state. And so our final state machine looks like this. We start off in the disconnected state. We connect initially, we succeed. We enter or try to enter a call. So we are in a call, and then suddenly an interrupt occurs. We lose network connectivity. This takes us to the retry substate within the overall connecting state. And if we retry and the connection is once again established, notice now that we will transition all the way back to where we left off in a history state. And the history remembers that we were in a session and had joined successfully, which allows us to resubscribe to audio video streams and get a list of all the members in our group and so forth. Again, there's more involved here, and there are a number of pieces still left out, but it's very easy to get a conceptual feel for what is needed to make our application behave as expected, as needed. So now we've enabled the retry logic to be modeled as well, and we can step through it and observe what's happening. So I do have a quick demo for this in action. So I'll have to switch example. So if you want to try this out on your own, we can simply import a different root component. This example uses the Agora service for real-time communication, real-time messaging. So that's why it's named that way. Agora is a real-time service that you can subscribe to or sign up for and use. So here is a simple, here is our DevTool view. So we're in the disconnected state. We log in, and we get all the way to connected. We are now idle, from which we can log out to disconnect entirely, or we can make sure that we receive a call. So here is a sample app that I've used to simulate a host that invites the web client to a call. So I'll send something to invite the client, and the client gets that join call event. We're now in the pending state where I will accept and enter the call state, the nested call state. And the session state is taking care of the session management. The stream part is not active right now. I don't have any logic for it, but it's there when we want to implement further. So now, well, you can see we're entire nested hierarchy of states. We're in the connected state. Further down in the nested call state, we have joined the session, and where if we had more logic for the stream part, we would see that as well. And if the host now joins the group, you'll see that the membership list has been updated. And we can see that our context, where we're storing this, our context keeps track of the members that we have in our group, in our call. And if I leave, where should I end up? I leave the call. I'm the join state. Clicking leave will take me to the connected idle state. And it does. And if I log out completely, that is, I disconnect, I should end up in the disconnected state, which also happens. So, what's the takeaway from this example? Well, we had a bit more details about states. They can be nested, they can be hierarchical. That's a good way for us to structure more complex state logic. We could have parallel states that are active at the same time. That's often a good way also to model things. And we can have a history. We can remember where we left off. And if we want transition and take large transitions, we can do that. We can remember where we left off and continue in that state when the state machine sort of resumes, like we did with the network reconnectivity. I haven't mentioned something called child machines, but as you noticed, there's a lot of things going on here, and the definition gets to be more and more complex. It's possible, for example, to extract everything that has to do with the call state, the nested call state, and put that in its own machine. And that machine can take care and represent everything that has to do with the call state. That is one good approach to better structure your overall state logic. You have many smaller state machines that can evoke and talk to each other. So more details about states, and again, state machines, child machines are one approach to better structure your overall state management. So I want to summarize that state machines sort of pushes us to be more formal when we reason about our behavior in our app, but it's good to capture complexity as it exists and as it grows in our apps. And that's what state machines allows us to do. The XState library and the visualizer especially gives us what we need. And it's pretty comprehensive for implementing and working with state machines instead of trying to roll your own. Now, this, as you might gather, you need to become more acquainted with this library, the terminology, the tools, the technology in itself. So a bit more in terms of learning, maybe planning. But I highly recommend it though, to make this investment, because the payoff, the reward is significant. It scales very well as your application grows. And with that, I would like to thank you very much for listening. Again, you can reach me, any questions that you might have. The code is, that's the full repo. So it's also shared in the chat. And again, you can visit the XState site to read more about it. And I also want to plug another webinar that I will conduct in March. It's going to be a React Ask Me Anything. So you'll be able to send me a lot of questions about everything that bugs you about React. And I'll try to go through them and show solutions and discuss things that you send in. So again, thank you. And if you have any questions, I'll be happy to answer them. So I got a question about how does state and XState relate to something like Redux? It's a very good question. Redux is also state management, but the word state means something else in Redux. For me, at least, state in Redux is not equivalent, but more similar to the context in a state machine. You can sort of approximate a state machine with Redux, but it's not really built for it. One thing that is you may surmise is that when we are declaring states, we're switching on the event that occurs, or I'm sorry, on the state that is we're in, and then we look at what event occurs and what the transition has to be. In Redux, we switch on actions. We don't switch on states. We switch on actions to update our state. But in XState, we switch on states. So here are a number of states. You can think of this as a switch statement. And if we're in this state and this event occurs, then this transition needs to happen. But more basically, or rudimentary, the context part here is what I think about as state in Redux. But it's sort of baked in XState. So you get the state machine concept implemented, as well as contextual data or Redux state handled as well. So it's not exclusive. You can still use Redux and state machines simultaneously. But I find it that the XState and state machines sort of cover what I need in terms of both managing data and the actual discrete finite states that I have in my app. Very good question, though. Thank you. Yeah, I've got a question about automating testing of all states, like Graph Walker. Yeah, if you have a definition like we do have here of a state machine, you can perform all sorts of automation on it. You can test various states that things given certain inputs do occur or not. You can do analytics, predictive analytics on certain transitions, maybe to personalize for individual users that visit your app. So given this definition, starting up a state machine with it, you can perform a number of automation tasks that you find suitable in your scenarios. And I will link to a talk from the creator of this library. He mentions more about how to do such automation and testing of your states. And as I mentioned, the sample code is available to you. In terms of this WebRTC app, you will have to sign up for Agora and register an account and a project, but it's there for you to try out if you so desire. But I encourage you to look more at XState if you find yourself sort of lost in the explosion of state events you might have in your project or app. Actual XState site. It's very pretty well done, and the documentation is excellent, and the guides will detail everything that I mentioned during this talk and introduce a bit more about how to implement state machines and various actions and services that you can work with. So I highly recommend perusing the documentation as well. Again, there is a learning curve, but I'm heavily invested in XState now, so I find it to be a good use of your time and resources. Can a state machine be shared between several components? Yes. So one state machine can be started in, here we start a task machine in one component. You can start the same machine in another component using the same code. But the more common use case is where you have a lot of state logic, which you break up into smaller machines. So you often have a parent or a few parent machines and a number of child machines. And then you can pass things that you need from the parent to the child, like context data. So you would have an app component running a task machine. And in terms of the call state, remember the call state, it was sort of highly involved. You could break that out into a child machine, call it call machine. And that call machine would be instantiated and run in another component. And if things have to be passed from the parent to the child, you could do that and also communicate back from the child to the parent. So we found ourselves with a few parent machines, like 4 parent machines at the most, but a number of child machines. And that gave us a better feel for working with all of our state and events. So I haven't seen the same state machine being run in multiple components, but as in our case, in our project and elsewhere, you break up your entire state logic into multiple machines and run them in different components. Unfortunately, I don't think you can actually have 2 machines running in this tool right now. I could be wrong, but I don't think you can visualize right now if you had a child machine for the call states. So if you're in the connected state in several components, should I pass in props? Yep, that's one way to do it. You can have an overall parent machine dealing with the connectivity part. And if you have to know about things in other components and subcomponents, you can pass that context information or the state as props. So you would, this information, whether a state is in the pending or failure or success state, you could pass that as a prop to a child component that you render as part of this component. But I would recommend when you start out, if you do start out, which again I recommend, find a piece of your app which sort of might be interesting to just convert into a XState thingy, or if you do have something that actually keeps you up at night, try to take that part, small part, hopefully in your application, and try to convert it into using XState and learn how to build state machines that way, instead of trying to introduce it into as a major foundation in your app as it currently exists. That way you get a feel for it and see how many machines you might end up with, what you need to pass around and so forth. So the task executor was a good example of this. It's pretty isolated and reusable as well. But that would be my approach, to start slowly with a well-defined part, isolated part of your app, and try to make XState happen with it. Any other burning questions? Well, might be interesting. What happened to my project? Did it work out okay? It did. We successfully introduced XState over several months, and we're pretty happy with the result. And funny thing that happens, if you define a state machine, like we've done, as a more abstract model, turns out that not only developers are interested in this stuff, in using this tool. The client had, of course, a lot of domain knowledge. So we sort of copy-pasted and sent a link of this thing to them and let them play around with it. Turns out that they, as domain experts, have a lot of more details about what we actually need to introduce in the state machine than we as developers did. So the client, domain experts contributed to the state machine definition, events and states that we didn't think of entirely on our own. So this definition ended up in version control on GitHub. And the client was able to add to it over time. That was a huge win for us. They could visualize, test it, play around with it. And after a quick session between us as developers and the client, we were able to incorporate their changes into the app. So that turned out to be a great thing to when you have to involve other stakeholders in the project. And it gets sort of fun after a while. It's fun to have a tool to play around with, actually follow the transitions in your model. All right. If there aren't any more questions, I'll end on that note. So thank you for, again, listening and all the excellent questions. Look out for my React AMA. Will be more details about that soon. And thank you. Hope to see you soon.